Today we're starting Activity 5, which is about distance and midpoint formulas. Lesson 5-1 is finding distance on the coordinate plane. Our learning goals are to first find the distance formula, and then to use the distance formula to find the distance between 2 points drawn on a grid. In the last activity, we used number lines to find distance and determine midpoint. To find the distance between two dots on a number line, it is as straightforward as subtracting the two numbers where the dots are. On a coordinate grid, we also use subtraction to find distances, but because points could be positioned diagonally to each other, it's going to be a little more complicated to find the distance. So in this activity, we're going to discuss the process. As an example, let's find the distance between point P and point Q. Point P is at 1, 4. So first point at the origin and locate 1, 4. The first number in the parentheses is x, the other number is y. 1, 4 is right 1, up 4, here's the dot, and this is point P. Now let's find point Q at 13, 9. Go over to 13 on the x-axis, and then go upwards until you reach 9 on the y-axis. Here's the dot, and let's label it Q. This is at 13, 9, and point P was at 1, 4. We want to find the distance between P and Q. That's equivalent to finding the length of the segment that connects P and Q. So I'm going to draw that segment in. To find that diagonal distance, we want to create a right triangle on the grid by coming down from point Q and coming to the right from point P, creating a 90-degree angle here. Now we have a right triangle. With a right triangle, we can use the Pythagorean theorem to find the hypotenuse. To use the Pythagorean theorem, we need to know the altitude or height of the triangle. The letter A is used to represent the altitude of a triangle. How tall is the triangle? It is 1, 2, 3, 4, 5 units tall. Now I want you to notice that we can find the 5 units by counting the grid squares or by using the y-coordinates of the points. That y-coordinate is 9 and that y-coordinate is 4. If you subtract 9 and 4, that makes 5. That 5 comes from subtracting 9 subtract 4. Using the y-coordinate of point Q and subtracting the y-coordinate of point P. If we make symbols to represent that, we might say take the y-coordinate of the second point and subtract the y-coordinate of the first point. 9 subtract 4 makes the altitude of the triangle 5 units. The bottom of the triangle is called the base, and it's a lowercase b in the Pythagorean theorem. How long is that? We'll start at this dot and count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The base is 12 units long. We could also use the x-coordinates of the ordered pairs to find that the base was 12 units long. This x value is 13, and this x value is 1. We could go 13 subtract 1. If we try to represent this in symbols, it's like saying, let's use the x-coordinate of the second point and subtract the x-coordinate of the first point. Now over here on the left side of the screen, let's show out the work that we used to find the length of segment PQ, which using the Pythagorean theorem is represented with a lowercase c. It looks like this. C squared equals a squared plus b squared. This relationship is true for all right triangles, that the hypotenuse squared is equal to the sum of each leg squared. Let's make some substitutions here. C squared equals, remember that we had figured out that a was 5, so 5 squared. And we had figured out that b was 12, 12 squared. Now let's work this out. 5 squared is 25, 12 squared is 144. 25 add 144 is 169. And to solve for C, we remove squaring using a square root. The square root of 169 turns out to be 13. 13 times 13 is 169. We figured out how long it is from P to Q. We found the distance from P to Q. Here are some check your understanding questions, so I'll pause the video for you to work on these. I suggest that you make a grid picture, graph the points, and then use the Pythagorean theorem, find out the values of A and B to help you get the answer for the distance. Here's the answer for number 9. Explain how you would find the distance between points J and K. J is at -3, 6. So left 3, up 6. I'm going to locate J right here. K is at 3, 14. Right 3, up 14. K is located here. Draw a segment connecting J and K. The next thing we want to do is create a right triangle. So we want to drop straight down from point K and go to the right from J to create a 90-degree angle here. The altitude of the triangle is the lowercase a in the Pythagorean theorem. We need to know how high the triangle is. We can find that by subtracting the y-coordinates of the points. Point K is at a height of 14. J is at a height of 6. So we can go 14 subtract 6 to find out that the triangle is 8 units tall. Across the bottom of the triangle is the lowercase b, the base. We could subtract the x-coordinates to find how long that is. This spot here has an x value of 3. Point J has an x value of -3. We can subtract those. 3 subtract -3, that's 6. JK is the lowercase c in the Pythagorean theorem. So here's the Pythagorean theorem work. C squared equals a squared plus b squared. Let's substitute 8 in for A and 6 in for B. Now we have c squared equals 64 plus 36. C squared equals 100. Now take a square root of 100 to find out that the answer is 10. JK is 10 units long. Okay, next I'm going to pause the video again for you to work on number 10. Do it in the same way we just tackled number 9. You might draw a little grid to help you visually see where the dots are, but the key is to use the Pythagorean theorem, which is this math formula. So to use that formula, you have to find the altitude of the triangle and find the base of the triangle. Here's the answer for 10 on the side of the screen. I've located point M at 9, -5 and point N at -11, 10. Now let's create a right triangle connecting these dots. Drop down from N until you reach the same height on the grid as where point M is. And then draw sideways from point M until you reach that other green line. When it touches right there, we want that to look like a 90-degree box. Then connect N and M together with a diagonal segment. This diagonal segment is called the hypotenuse of the right triangle, and it can be represented with a lowercase c in the Pythagorean theorem. This up and down side is the lowercase a, the altitude of the triangle. How tall is it? We could count the black marks on the y-axis or subtract the y-coordinates to find that height. This y-coordinate is 10. On the other ordered pair, this y-coordinate is -5. How far is it from 10 to -5? 10 subtract -5 is 15 units. Lowercase a is 15. The bottom of the green triangle is the lowercase b, the base of the triangle. We need to know how long it is. We can count little marks along the x-axis going from -11 all the way to 9, or subtract the x-coordinates. That x-coordinate is -11 and that one is 9. Let's subtract those. 9 subtract -11. That is 20 units. So lowercase b is 20. Now we can use the Pythagorean theorem. C squared equals a squared plus b squared. Fill in 15 for a and fill in 20 for b. Because these numbers are starting to get a little large, you might need to use a calculator on this. 15 squared is 225. 20 squared is 400. Therefore, c squared is 625. To find c, we do the square root of 625. That happens to be 25, because 25 times 25 is 625. We have figured out that mn is 25 units long. Our technique is to use the Pythagorean theorem and to use x and y coordinates to find values for a and b. Although the method we just learned for finding distance between points will always work, it might not be practical to plot points on a coordinate plane. What if the coordinates were really large numbers? We wouldn't want to draw a grid and have to put so many marks on there and then draw a picture. Instead, we can use algebraic methods to derive a formula for finding the distance between points. To do this, we're going to use variable symbols to represent the numbers for our coordinates. The first point, whether it's called point A, point M, point X, whatever it is in a math problem, we can use the symbols x1 and y1 to represent its coordinates. The second point in our picture, regardless of what letter it's called, we can use the symbols x2 and y2 to represent its coordinates. Number 12, write an expression for the length of the horizontal leg of a right triangle. Horizontal is across. It's the one that we said was lowercase b, and our formula could be x2 minus x1. Number 13, write an expression for the length of the vertical leg. The vertical leg was the up and down side of the triangle, the one that we labeled lowercase a, and it could be y2 minus y1. Number 14, use the Pythagorean theorem to write an expression for the length of the hypotenuse of a triangle. The Pythagorean theorem is c squared equals a squared plus b squared, but using those new formulas, the letter a could be written as x2 minus x1, and the letter b could be expressed as y2 minus y1. Recall that to get the answer for c, we need to do a square root, and so I'm going to make a very large square root symbol under which I have those formulas. x2 minus x1 squared plus y2 minus y1 squared. This is called the distance formula. I'm going to pause the video for you to put this in your notes. It's going to be a key math formula that you're going to use all year long in geometry class. Number 16, use the formula we wrote to find the distance between these points. We're not going to draw a picture this time. We're just going to find the answer with the formula. Remember that the first point gets the symbols x1, y1. The second point gets the symbols x2, y2. Here was the distance formula we just wrote. The distance is equal to a big old square root symbol. And then inside here, x2 minus x1 squared plus y2 minus y1 squared. You have to correctly write that formula down to be able to get the rest of the problem right. Okay, let's do some work on this. There's this big square root symbol. We're going to make some substitutions. x2 is -3 minus x1 is 12. In the other parentheses, y2 is 7 minus y1 is negative 5. Notice the parentheses, notice the squaring, notice the plus sign separating the parentheses. Okay, next step. Let's do some more work inside the big square root symbol. Negative 3 subtract 12 is negative 15. Over here in the other parentheses, 7 subtract negative 5 is 12. Notice the parentheses, notice the squaring, notice the plus sign between the parentheses. Next step. Negative 15 squared. Negative 15 times negative 15 is 225, or use a calculator. Plus 12 squared is 144. 12 times 12 is 144. Now let's add those two things together under the square root. That makes 369. The final step is to actually evaluate the square root of 369. Let's use a calculator for that. The result, rounded to one decimal place, is 19.2 units. The distance between that ordered pair and that ordered pair, without drawing a picture, is 19.2 units. And we were able to get that answer by using the distance formula. I'm going to pause the video here for you to copy down all of these work steps in number 16. This will give you something to work from when you need to try these on your own. Here are the check your understanding questions. I want you to do number 17A on your own, but don't try 17B yet until you've seen whether you got 17A correct. Here's the answer for 17A. The first thing you should have written down was the distance formula. Please check that you have every single one of those symbols correct. Parentheses, the plus sign, all these little tiny numbers in the bottom corners of the letters. The next step is when you substitute values for those. So x2 is 7, x1 is negative 8, y2 is negative 3, y1 is 5. Now come the subtractions. 7 subtract negative 8 is 15. Negative 3 subtract 5 is negative 8. Next comes the squaring. 15 squared is 225. Negative 8 squared is 64. Next comes the adding. That makes 289. Final step on a calculator, the square root of 289 is 17. So the distance between these two ordered pairs in problem A is 17 units. Please try question B on your own. And here's the answer for 17B. Start by writing out the distance formula. x2 is 8, x1 is 3, y2 is 3, y1 is 8. 8 subtract 3 is 5, and over on this side, 3 subtract 8 is negative 5. 5 squared is 25. Negative 5 squared is also 25. 25 plus 25 makes 50, and then do the square root of 50 to get 7.1. That's the distance between those two dots. In this lesson, we derived the distance formula. The word derive means we created the distance formula. Then we used the distance formula to find the distance between points, and we didn't even have to draw a picture of the points to do this.